Hi everyone, my name is Andrew Larson. Thank you for coming to my presentation. Let's get started. So we sourced our US data from the COVID tracking project and the Colorado data from the Colorado Department of Public Health and Environment. We pulled this data as of 7/17, and we had to cut the US data off as of 3/8 because it's the first day we had all 50 datas tracking their data. You can see the cumulative positive percentage total cases and total deaths as of 7/17 to the right. And this positive percentage statistic is the number of positive tests over the number of total tests. In our EDA, we looked at daily deaths, daily positive tests, and daily positive percent. And they were all intercorrelated, so we wanted to bring those all into our multivariate time series analysis forecasts. But we start with our univariate models. We start with our ARMA model for Colorado. Colorado, we decided, was stationary. There was no evidence of non-stationarity in the factor tables, realization, sample autocorrelations, or Parsum window. So we used AIC to fit an ARMA model. It was determined that an 8.2 and a 7.1 model was the lowest AIC. BIC suggested an AR1 model, but this did not pass the Young box test. We ended up with this ARMA 8.2 and ARMA 7.1 model. Both passed the Young box test. The ARMA 7.1 model did have a significantly lower ASC though. You can see the forecast to the right. The short-term forecasts don't have a lot of difference as far as structure goes, but the 7.1 model is significantly lower as far as predictions of cases goes. This is not true for long-term forecasts. They do not have a similar structure. The 8.2 model has kind of a sinusoidal behavior, while the 7.1 model only damps to the mean. We then looked at a neural network. We had lags of 1 in 4 of new cases as the inputs. These inputs affect the single hidden layer using weights and biases, and then the hidden layer affects the output using their weights and biases. And we have an output. We trained 50 of these models, and we took the median in order to create our forecasts. These forecasts had an ASC of about 22,000. We also used the 95th and the 5th percentile in order to create our prediction limits. This forecast drops to the mean extremely slowly, so instead of using the MLP in our ensemble, we used the two ARMA models. You can see that the ASC is about 22,000. The short-term trend is directly in between the two because they have a similar structure, while the long-term is just a sinusoidal trend that is damped closer to the mean. We then looked at ARIMA models for the US. It turned out the US data was non-stationary. We looked at the realization, autocorrelations, and Parsum window, as well as the factor tables in order to come to this conclusion. We took to the first difference, and this looked stationary, so we decided to build an ARIMA P1Q model. We had an ARIMA 612 model and an ARIMA 810 model. We could have also used an ARIMA 712 model, but we decided that the 712 model would have had predictions that were too similar to the ARIMA 612 model. So we have our two models here. Both passed the Young box test. Both have rolling window ASCs of about 31 to 32 million. Here are the forecasts. Very similar forecasts, ironically. The short-term forecasts both have this swooping behavior, and the long-term forecasts both have this sinusoidal behavior, but the 810 model has a quicker damping sinusoidal behavior than the 612 model. We then created a univariate MLP model, ended up with an ASC of 65 million with hidden nodes of 4, lags of 2, 3, and 4 of US new cases in the model. We have a forecast that has less wiggle than the ARIMA. It's linear in the long term. It's much sharper. Because of the ASC, we use the two ARIMA forecasts in our ensemble. We took the average of the two for prediction limits in the forecasts. We ended up with an ASC that was significantly lower, actually, that ended up being about 21 million. And in the long term, we kind of have a damped wiggle trend, while in the short term, it is directly between the two ARIMA models, and it still has that swooping behavior. So now we look at our multivariate models. We started with a VAR model for Colorado. VAR is vector autoregression. What this is it takes lags of different variables and uses it to predict one variable. In this case, we're using lags of new cases, new tests, new deaths, and positive percentage in order to predict new cases. We ended up using 4 lags because that's what the VAR select decided on. 15 lags were put into the call because of how far back positive percent and new cases seem to be correlated. ended up with 4. K equals 24, K equals 48, both passed the Young box test, and we ended up with an ASC of about 17,000. Unfortunately, these forecasts damp really quickly to the mean, so we move on to our multivariate MLP model. So the multivariate part of this is just we include lags of other variables in the input. So we ended up with new cases, positive percent, new test lags in here, and 5 hidden nodes, and we ended up with an ASC of about 18,000. You can see that these are very different forecasts than any other Colorado model that we've created. There's a third peak and then a drop in the short-term forecast, and the linear trend starting in about July is linearly increasing, and it has quite a bit of noise. The ensemble is the average of the VAR and MLP model with an ASC of about 18,000. The VAR forecasts the mean, while the VAR forecasts not the mean. So the VAR forecasts, or the ensemble forecast, is just the VAR forecast that's damped to the mean. Our VAR model for the US, we ended up with 6 lags. We ended up putting 18 into the call because of how far back new deaths and new cases was correlated. We ended up with 6 lags because we had 1, 3, 6, and 18 as the 4 metrics predicted that we should use. 1 and 3 did not pass the Young box test, while 18 and 6 did, but 18 was too far back to use, so we ended up using 6. This passes the Young box test at K equals 24 and 48. We end up with an ASC of about 46 million. We have a swoop in the short term. You can see that in the short-term VAR, and it damps to a value that isn't the mean, so it kind of slowly increases and damps that sinusoidal trend over time to a limit. We ended up with a multivariate MLP model as well, with 5 hidden layers and 8 inputs of new cases, positive percent, new tests, and new death lags. Very high ASE, and that's due to this runaway forecasting behavior. And this runaway forecasting behavior is also in the ensemble forecasts. The MLP forecast just dominates this trend, end up with an ASE of about 1.1 billion. So the best ASE overall for the US was the ensemble of the ARIMA models, while for Colorado was the ARMA 7.1 models. All of these forecasts are useful. It just depends on how you believe that cases in the US and Colorado are going to behave. Thank you so much for coming to my presentation. I hope you have a great day.